Magicians all over the world are out to impress their audiences, and one of the biggest tricks they have up their sleeve is to make someone levitate. So here within the confines of our Canyon Point Lounge, we have the world famous magician, Dark Temptation, who's going to attempt to levitate what looks like in excess of 300 pounds. Let's see how it goes.
I am Dark Temptation, and I am going to make your filthy soul levitate. Abracadabra, hocus pocus, bibbidi bobbidi boo.
Well, that didn't work out as planned, but fortunately, what magic can't do, science can. So we've all seen the cartoon Jetsons, and what's the first thing you think about when you think of the Jetsons? Flying cars, right? Impossible, you say? I say no. Technically, we already have flying trains using the concept of magnetic levitation. How this works is, you have an electromagnetic track through which you can change the current, and that changes the magnetic field of the track. Now this magnetic field repels permanent magnets in the undercarriage of the train, which makes it look like the train is floating in the air.
Now, of course, the problem of propulsion is solved using the concept of electromagnetic suspension, but we also have the issue of propulsion in the forward and the backward direction along the track, and that is solved using a linear motor. So what a linear motor is that it's basically a normal electrical induction motor that causes linear motion instead of the normal rotary motion. So at the beginning of this quarter, our idea was to design and develop a linear motor, and also to construct the guide rails necessary to make a magnetic train, a maglev train levitate. However, we spoke to Professor Simon of the physics department, who's an expert in the field of magnetic levitation, and he was of the opinion that this project was a bit too ambitious for the 4-week time frame that we had. However, we did not want to let go of the idea, so what we decided was to build a static magnetic levitator with an equivalent control system.
How the static levitator works is, you have a coil through which you pass current, and that changes the magnetic field, and you have your object levitating over here, and the magnetic force balances the weight of the object. And if you replace this object with a heavier object, then the optical control system that we have would compensate for that by changing the current through the magnetic coil, and so even the heavier object would levitate at another distance. So here's a video of our project in action. So this is our magnetic levitator circuit. I have an electromagnet over here, which is a coil wound around a screw. On the right side there is an infrared LED, and on the left side there are two phototransistors. The output of the phototransistors goes to the input of an op-amp, and as we know, the op-amp is a difference amplifier, so it's going to amplify the voltage difference between the two phototransistors. Initially, when there's nothing blocking the beam from the infrared LED to the phototransistors, the difference in voltage across the phototransistors is going to be 0, and so the output of the op-amp is going to be 0. But as soon as I put something that blocks the beam from the infrared LED, that's going to change the voltage across one of the phototransistors, and so now the output of the op-amp is going to change. This output goes as input to another op-amp, which drives the current through the coil, and so the current is going to change, and so the magnetic field of the coil is going to change. And I'm going to switch on the circuit now. As you can see, there's a magnetic field created, and so the screw is supposed to levitate over here, but the resistance of the coil is too high, so we cannot generate a strong enough magnetic field to make the screw levitate. We tried experimenting with different coils of different resistances, but given the current and voltage limitations in the lab, we could not generate a strong enough magnetic field to make the screw levitate. So as long as I maintain minimal contact with the screw, it's going to stay there and flutter, but as soon as I take my hand away, it's going to fall down. And so it ended up being a case of so close but yet so far.